Hello students, welcome to Sarasa classes. Now today's topic, another vital topic from chemical bonding, and that is going to be dipole moment. We have to predict which molecules have zero dipole moment or non-zero dipole moment. Okay, so over here dipole moment is represented by the symbol mu, and the mu dipole moment is basically the product of distance between the charges and the amount of charge E. So D is distance between the dipoles, that is the charges. So if we say there is a molecule like HCl, this is delta negative, this is delta positive. Okay, so this will be the charge. Okay, and that should be the direction of the dipole. The arrowhead will be pointing towards the negative end, and obviously when we say distance, so this is the bond distance over here between the charges. E is the charge. Okay, so what should be the unit of dipole in CGS unit? Okay, so the distance of bonds are in the range of 10 to the power 8 centimeter, and the unit of charge in CGS unit is going to be 4.8 into 10 to the power minus 10. ESU means electrostatic unit. So this is going to come out to be 48 into 10 to the power minus 18 ESU centimeter. So this is the unit for dipole moment in the CGS system. However, in the SI system, we will say unit of dipole moment is dBi and represented as D, and that is related to the coulomb meter, as in 3.33 into 10 to the power minus 30. C stands for coulomb and M stands for meter. So coulomb is the unit of charge in SI unit, and meter is the unit of distance in SI. Now we have been given some molecules over here. We'll take some examples. Suppose I am giving you the BeF2, which we know in its vapor state. Okay, it is having a linear structure. So which is the negative end over here? The fluorine being most electronegative will be delta minus, and the beryllium will be delta plus. So from the beryllium we will have one dipole directed towards the fluorine in the right hand side, and another dipole directed towards the fluorine in the left hand side. So the moment of this dipole, let's write that as BEF, and that dipole, which is also BEF, they are lying at an angle of 180 degree. So each of these individual dipole moments will cancel out each other, and so the resultant dipole moment will be 0 for BEF2. Similarly, if we take carbon dioxide, which again we know is having the linear structure, for that also negative charge will be on oxygen because it is more electronegative. Positive charge will be on carbon. So this is one CO dipole, That is another CO dipole. Again, if you see what is the angle between them, it is 180. So each of these CO dipoles will be cancelling out each other, and the resultant dipole moment for this molecule will be 0. So in totality, what we are saying, any molecule that is having a linear shape, and I'm writing few more examples such as CS2, okay, or the nitronium ion, which is NO2 plus, okay, these type of molecules will be having zero dipole moment. It can also be a complex ion, something like AgNH3 whole twice, this one, okay. From VBT, that is valence bond theory, we will know that this is also having linear shape. However, for molecules like say SO2, as we can see, they are bent or V-shaped. So here we will say these two dipole moments will not be cancelling it out each other. All right, they are having an angle between them very close to 120. So over here, the resultant dipole moment is not going to be equal to 0. All right. Similarly, if we take the NO2, for which we know this is the structure, all right, and that is the odd electron pair over here. Again, one can say that the resultant dipole moment of this molecule also will not be equal to 0, because these two dipoles over here and that, they are not cancelling out each other, okay. The angle between these two dipoles is very close to again 120, because NO2 is sp2 hybridized. So over here, the resultant dipole moment, we will say it is going to be again non-zero. Similarly, for NO2 minus also, we will provide the same conclusion, okay, which is obviously we will say this is like that. And here also we will say that the resultant dipole moment of this molecule, because the individual dipoles are having an angle of around just maybe a little bit more than 120, so we will say or less than 120 rather, we will say this particular molecule also will be having a resultant dipole moment on 0. Now, dipole moment of water, another molecule, very simple. We will say again, these are the lone pairs, okay, and as you can see here, the electronegative atom is oxygen, so the dipole moment is directed towards the oxygen. So these two, this one and this one, will add up with the lone pair moments over here, and again the resultant dipole moment, because this angle over here is around 104, so they are not cancelling out each other, but they are adding to each other, okay, and the resultant dipole moment over here is going to be non-zero. Let's take a few more examples such as AB3 type molecules. So over here we have taken a BF3, and what we will say that these are the more electronegative atoms, so obviously the dipoles will be acting or directed towards the fluorine atoms. Now, because the angle out here is 120, you have to understand that the resultant of this two dipoles over here if you use the formula, say we are calling this as mu r, okay, and this one is suppose mu1 and this is suppose again mu1. This one also we are calling as mu1. So what will happen over here? We will say the resultant mu r is nothing but mu1 square plus mu1 square mu1 into mu1 cos 120. So this is going to be mu1 square, and cos 120 means half minus half. So this becomes minus mu1 square. So the resultant dipole moment is basically equal to mu1. This one is equal to this one. So we are saying this is mu1, and this one out here, this is also mu1. Now if you look at the resultant, that is the angle between the resultant mu r and mu1, this is nothing but 180. Because it is 180, so again this one will cancel out with this one, so the resultant dipole moment of BF3 will be equal to 0. Okay. Another similar case will be found in case of SO3, because it is also having the trigonal planar shape. Okay. So any molecule that is having a trigonal planar shape will also be having the dipole moment equal to 0. Okay. Now let us compare dipole moments of NH3 and dipole moments of NF3. The question out here is, which is having more dipole moment, NH3 or NF3? Now as you can see, nitrogen is more electronegative, so the dipole moments are directed towards the nitrogen, which will again add up with the lone pair moment. Out here the lone pair moment is in this direction, whereas fluorine being more electronegative, the dipole moment is directed from the nitrogen towards the fluorine, like that. So here the lone pair moment in NF3 is opposite to mu NF, okay, resultant. However, in ammonia we will say this lone pair moment is in same direction to resultant NH lone pair moment. Okay, let me write that properly, NH lone pair moment. So that means this one will add with that one, this resultant will add with the lone pair moment, so it will be having a greater value. So in that sense, what we will say, that mu NH3 will be having a more dipole moment than the mu NF3. Now if you were to consider a molecule which we had discussed in the back bonding case, so let's write that NSiMe3 whole thrice. Now since again the actual geometry of this molecule is again trigonal planar, that is, it can be represented in the following manner. We will use the same logic that we have used for SO3 or for BF3. So for this molecule also, which we know the lone pair on this nitrogen is being distributed to the d orbitals of the silicon molecule, silicon atom, right, via back bonding. So its shape over here is trigonal planar, and the angle over here is again 120 between the SI bonds over here. So again the resultant dipole moment of this molecule will be 0. Okay. Now let us take some examples of tetrahedral molecules now. So I have a sulfate, and from the concept of resonance or delocalization, we know that all the bonds over here are of equal length. Okay, that means this pi electron density over here is actually distributed to all the SO bonds. Okay, that is what we know. Just like that. Sorry, it is distributed like that. Okay, and this is the minus charge on each of them. Now, what was the resultant charge over here? -2. How many oxygens are there? 4. So this is basically what? Equal to minus half. So each of these oxygen atom will be having minus half units of charge. Okay. Now again over here, the dipole moments will be directed from sulfur to nitrogen. So this is one of that SO bond moment. Okay. So this is mu SO say, and these ones are directed like that. Now, important to understand that this one, and this one, the resultant of that, okay, just remember the resultant of that, all three SO bonds is basically equal to this one, okay. I'm not showing the calculation over here, okay, but just remember this is equal, and so eventually we will say these two will cancel out each other, okay. Now, the next example that we are going to take is that of a perchlorate ion. So what is the structure of a perchlorate ion? We will say this, and as we know, this is the resonance structure, but actually the hybrid structure is going to have, that is a resonance hybrid structure, is going to have all the bonds of equal length, okay, something like that. All right, and the charges present on each of the oxygen will be -1/4. Okay, now if you think again, just like the sulfate, the ClO moment, this moment is actually opposite to the resultant dipole moment from the ClO, this one, and that one. So again we will say that the mu ClO resultant is exactly at a 180 angle with the mu ClO moment for this particular bond. Okay, and again we will say, so the resultant dipole moment of ClO4 minus is going to be 0. Few more examples we are going to do over here using regular and non-regular structures, or where the substituents vary. Let's have a look. Now I have taken over here the PCl4 plus. PCl4 plus means the structure is going to be regular and tetrahedral, and using the logic that we have learned for SO4 2 minus or ClO4 minus, out here also we will conclude that this particular bond moment of PCl is going to be lying exactly opposite or at a 180 to the resultant bond moment for PCl, this one, and this one. So this mu PCl resultant is exactly opposite to this particular mu PCl, and hence the total bond dipole moment for this particular molecule will be equal to 0. Let us check POCl3. Now POCl3, this one, so it is having the following structure as I am drawing. Okay, now one can see that apart from the 3 chlorine, there is a oxygen over here. So obviously if we take the PO bond dipole moment, and we can think this will be lying opposite to the resultant PCl bond moment coming from this one, and this one. So if that resultant is lying in this direction, which is exactly 180. Now since this is PCl, the resultant moment for this dipole, that dipole, and that dipole bond, obviously. So, and this is basically mu PO. Now since this one and that one are not equal, so obviously the resultant dipole moment for POCl3 is going to be not equal to 0. Okay. Similarly, if we take PCl3, which is having a lone pair, so here the lone pair moment is lying opposite to the resultant mu PCl, and since these two are lying at a 180 degree to each other, right, and not equal to each other, okay, the lone pair moment is not going to be equal to the PCl resultant bond pair moment. So over here also we will say the the actual dipole moment of this particular molecule is going to be not equal to 0. So this is how we have to find out. Let us take some organic systems, molecules. Now over here, suppose you have been given a benzene, so we will say it is having dipole moment 0. If you have given chlorobenzene, now the dipole will be acting in that direction because of the higher electronegativity of chlorine. So this is obviously we will say dipole moment is not equal to 0. But now if you have chlorine attached to the para position, so this moment and that moment are lying at an angle of 180 degree. So the resultant dipole moment of this molecule will be equal to 0. Okay, so this is 0. For this one, when the two chlorine are lying like this, which is we will say ortho to each other, and we can take another case in which they are lying meta to each other. So if we now want to compare, we will say obviously the dipole moment over here is going to be not equal to 0, and for this one also it will be not equal to 0 because this is the direction of the dipole moment. like that, and here also. So now if you think what is the angle between these two particular dipoles, so you just extend the line and you can think this angle is going to be what? It will be 60. Okay, that is what it will be. But what about this one? If you check, so we will say this angle out here now, will it be 60? It will be rather more than 60. We will say it will be around 120, this angle over here. Okay, so now if you calculate the dipole moment for this molecule, what we will say? This will come out, say this is mu1 and that is also mu1, right? So it is mu1 square plus mu1 square plus 2 mu1 into mu1 cos 120. So this is 2 mu1 square minus cos 120 is minus half. So we will say, so the resultant dipole moment is going to be only mu1 square. What about this one? We will say again it is mu1 and this is also say mu1. Okay, now using the same formula over here, it will be basically mu square mu1 square mu1 square 2 mu1 cos 60. Cos 60 is what? Half. So basically this becomes 2 mu1 square plus mu1 square, that is going to be 3 mu1 square. So obviously this particular molecule is having greater dipole moment than this molecule. Okay, so if you arrange and call these molecules as 1, this one as 2 and this one as 3, and if you are asked arrange them according to increasing dipole moment, what will you say? You will say 2 is greater than 3, which is greater than obviously 1. Alright, that is how you have to answer this type of questions. Now over here in this particular next part of the lecture, we will deal with something called calculation of percent of ionic character in polar covalent molecules, obviously. Now suppose the question given to us is HCl has a dipole moment of 1.03 into 10 to the power minus 18 ESU, and its bond length is found to be 1.27 into 10 to the power minus 8 centimeter. Okay, so we will first find out what is mu. Alright, so mu we know it is basically Q into D, that is charge into distance. Okay, and now if we calculate the charge, it will be mu by D, and so we will write 1.03 into 10 to the power minus 18 divided by 1.27 into 10 to the power minus 8. That will give us a charge of 0.8. If we do the math, simply ESU. Okay, so this is basically ESU centimeter, okay, the unit. So now if we consider HCl to be purely ionic, Okay, then the charge will be 4.8 into 10 to the power minus 10 ESU. Okay, so now if you have to calculate the percent of ionic character, so what is the observed charge? The one we found over here, this one. What is the theoretical charge? Obviously this one, because we are assuming it is purely ionic. So this is theoretical charge into 100. And that if we calculate, so we do the math over here. So this will give us something around 17%. Now, if the question was asked, what is the covalent character? So basically we will think it is 100 minus ionic character. And if you do the math, it will come out to be as 83%. Okay. So this is how we have to solve problems of this nature. And thanks for listening. Have a great day.